All right, beautifuls, we are starting chapter 1, section 1. And that is parent functions and transformations. There it is. Okay, parent functions and transformations. So a parent function is where it starts, and then transformations is how it changes. Does it slide? Does it reflect? Does it get narrow? Does it get wide? All that jazz. Okay, so I gave you these 6 graphs right here. What do we think? Your options were constant, linear, absolute value, quadratic, square root, or exponential. So which one did you label as constant? Number 3? Yes, I agree. Good. I'm going to turn this. All right, yeah, this was our constant, meaning it didn't change, it was flat, right? All right, which one did you label as linear? 6, good, the one right here below it. All right, which one did we label as absolute value? Number 1. Because it makes a V. Absolute values make a V. All right, which one did we label as a quadratic? Number 5. Here's our quadratic. Which one did we label as a square root? 2. Oh, look at that. You're a good guesser. And then that leaves exponential with number 4 down here. Good job. Very good. So now I want you, so you did that. You sorted the parent functions. So yeah, now you have them labeled. Now I want you to actually talk to your partner, okay? And I want you to sort them. Sort parent functions into groups, okay? No really wrong answer here, as long as you explain yourself, okay? So I want you to group them somehow, and then I want you to tell me the characteristics you chose to do that grouping. Okay, so talk to your partner. Okay, I like this discussions has fizzled. Dion, which ones are you talking about? 1 and 5. Okay, what do you like about 1 and? Okay. All right. Who wants to share another grouping that they did? Brennan, what you got?
1, 3, and 6, but no curves, and 2, 4, and 5 for curves.
Okay. 1, 3, and 6 are all straight lines. 1 is a combination of 2 different straight lines, right? But it's still straight, and the other one's curved. Good. Did anybody group anything else a different way? Dion, what you got?
2 and 4, does it kind of like go up at a curve?
Okay, they have curves going up, all right? Brianna. Okay, yeah, 3 and 6 are infinite lines, right? They go forever in both directions. There's no curves or anything in them. Good, these are all great. Did anybody say that 2 and 5 were inverses of each other? Yeah, square roots and squares. Right, they were inverses of each other. Did anybody maybe do 1 and 5 because they both had like a vertex? Possibly? Yeah? Yeah, you notice that? Kind of like bounced off somewhere? Good. Yeah, that's fine. Same thing. Good. Beautiful. So, functions that belong to the same family share key characteristics. This is your first blank. The parent function is the most basic function in a family. Functions in the same family are transformations of their parent function. So what you just identified is where all of our graphs start from, okay? We all come from parents. Everybody has parents. That's where you come from. So the parents were the OG, and then you are the transformation of your parents. Does that make sense? Okay. So the parent function is where we start, and then from there, and then transformation is how we move or alter the graph coming afterwards. Okay. So we have some parent functions listed here. I don't know if you even saw that was there or not. But you have your constant, your linear, your absolute value, and your quadratic. So it's not all 6, but there's 4 of them. What is underneath those? Domain and range. Do we remember these words? Ringing some bells? Don't forget them. They're here to stay. Okay. So looking at these, they all have a domain of all real numbers. What does that mean? First off, what is domain? My x values. Beautiful. What does all real numbers mean? Yeah, it means all of them. That it doesn't stop. It goes forever negative and forever positive, right? So do we see how the constant goes forever left, forever right? Linear, absolute value, quadratic. They have the arrows on both sides, correct? Looking at your parent functions to begin with, which one of those is not going to have that for their domain? The square root, because the square root can't go past what? What x value? It can't go past 0. Right? So see how it starts at the origin and then goes up and over? Because you can't plug in a negative x. Well, not yet. Into a square root. Okay? And then my range depends on my what values? Our y values. So here, that is typically different amongst all of them. So constants, it's going to be what the y value actually is. Linears, though, they forever go up and down. That's your y-axis, right? That goes up and down. So that one's going to be all real numbers. But my absolute value in quadratic, the parent function, the vertex, sits at the origin, right? So it's not going to go under the origin. So that's why it says y's have to be greater than or equal to 0. Because we start at 0 and then we go up for the parent function. Now, if it moves, that could change. But parent functions, they're not going to go below that 0. All right, we good? Sweet. Here we go. So what we're going to do now, you're going to identify what this parent function was, and then how does it compare to the parent function? Like how did it move? How did it alter itself? Okay. So first things first, what's the parent function? How did you know its absolute value? Looking at it. It's a V shape, right? It's a V shape, so we know it's an absolute value. Okay, so comparing this to the parent function that you have at 2 different places up here above you, how does it look different? And even gave me the function. How is it different? What do you think, Brennan?
It's moved up 1 and it's a little bit skinnier.
Yeah, it has moved up 1 and it's a little bit skinnier or narrow. Okay, look at the equation. So it went from absolute value of x, and now it's 2 absolute value of x plus 1. Do we remember doing these? This shouldn't be new information. Hopefully. Okay, so the graph is shifted up 1 and it is more narrow. Did the domain change for this absolute value function? Nope, it's still all real numbers. It's still going all the way left and all the way right. Did the range change for this? Yes, because now my y's have to be bigger than or equal to what? To the 1, because it got shifted up. My vertex moved, so my domain is fine, but my range has shifted. Okay, so we went, it is an absolute value. It's shifted up 1, and it's a more narrow V shape. Okay. Our domain did not change, but my range did. That's how we compare. When we compare, we do the common, what's the same, what's different. Yeah, think you can do some? I think you can. How about these guys? So we have number 1, number 2, they're on your paper. Identify what the parent function was. So what did it start off? And then how did it transform? Okay, how did it move? What is different? So the graph is there and the equation. So you could use either one to help you. Give you about 10 more seconds. All right, Josh, I'm going to come to you, friend. What parent function did number 1 come from? Like which one of those first 6 from our warm-up, which one of those would you use to label this? Linear, yes, there you go. Good, this is linear. Serena, how did it change? What do you think?
It went like 2 up.
Yes. No, perfect. It went up 2 units. Good. Did my domain change? No. Did my range change? No, it won't with lines, okay? Because they're going to forever go all the ways. They're good to go. All right, beautiful. Naya, what parent group is number 2 from? Quadratics. Beautiful. All right. Got a couple things going on there. We have a 1/4 and a -3. So there's definitely 2 transformations. Y'all see how I noticed that? Because it came from x squared. So this is new and this is new. That indicates 2 things have happened to it. Who wants to take a stab at what those 2 things might be? Abidon, what do you think? Okay, so it moved which way? 3 to the right. Good, so that -3 made it go 3 to the right. Okay, what do we think the 1/4 did, Brennan? Made it wider. Good. Is it coming back? Are we remembering transformations? Kind of? Yes? Okay. You tell me. What's up?
So when the -3, is it like, does it go through to the right instead of left because like the square?
It's because it's in parentheses is what's doing it. Yeah. So I always say inside opposite, and you'll hear me say it all year long. If it's inside parentheses, you actually do the opposite of what it was. Because the parent equation is actually x plus h. So because your plus h is now a -3, that's where the opposite comes in. Because the parent function had a plus there to begin with, so it got flipped. Yeah? Ready for the back? There's a back. Oh, yeah. Gotta have some more fun. All right, so some more fill in the blanks. A transformation is going to change the size, shape, position, or orientation of a graph. Okay? Specifically, a translation is the transformation that shifts the graph horizontally and or vertically, but the size, shape, orientation does not change. It's not going to rotate. Okay? It's not going to get wide or narrow. It just physically copy paste it somewhere else is what it's doing. All right, so look at example number 2. It says graph x minus 4 and its parent function, then describe the transformation. Okay, so we're moving right next to it. So first off, how do I graph the parent function? Well, what is the parent function? Where did it start off with? The parent function. It was just y equals x, right? This is a line. So the first thing you're going to graph is just y equals x, where we cut through the origin, and my slope is just a 1. It's very boring. That's the first thing you're going to graph on there. You can label it as parent. I know you probably don't have, if you had different colors, I would do a color for the parent and a color for the transformation. If you don't have that, I would label one as, just label parent and the other transformation. You could use OG if you want to for the original, and then T for transformation. However you want to identify it on your part so you know where it started and where it ended up. Okay, I'm going to call this guy parent. That's the parent function. So now we need to graph the transformation. So to have x minus 4 tells me that what happened?
Goes down.
It went down 4. Did my slope change? No. So my slope is the same, but now the whole thing has gone down 4. So instead of cutting through the origin, now it's cutting through the y-intercept of negative 4, but my slope is still 1. Remember bingo? Yes, this is when bingo kind of comes back and helps me. Okay. So this is our parent function. And they use g of x, so I can say this is g of x to show that that's the transformation. Yeah, good, easy. We can move on. Yes, okay. All right, example 3 is going to be an example of a reflection. Okay, a reflection is a transformation that flips the graph over a line called the line of reflection. Okay, a reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So we typically reflect over the x-axis or the y-axis, okay? But you can really reflect over anything. You can reflect over y equals x. That's how you actually do inverses, okay? You could reflect over the line y equals 3, okay, if told to do so. So you can reflect over anything. In an equation, though, what do you think represents a reflection in the equation? There's a certain symbol that does it, Dion. Please stop. What symbol usually indicates a reflection? What you got? Yeah, a negative sign, right? That's usually how it presents itself in an equation. So we're going to graph negative x squared and its parent function and then describe. So the first thing I got to do is I got to reflect, okay? But I can't reflect unless I know where it starts. So I'm going to make a little chart. You don't have to do this, okay? It's totally up to you. So to start off, I'm going to have some x's, okay? What is negative 2 squared? What is negative 1 squared? What is 0 squared? What's 1 squared? What's 2 squared? 4. So this is just a way to organize yourself. If you want to do it, you don't have to. It might come helpful when things get a little bit more complicated. So we know that that's the parent function. Nothing's changed yet. I have just plugged in x's into x squared. That is my parent function, okay? And it's going to look like this. Some of you might have been taught the speed graphing, the 1, 3, 5, maybe. When it comes to quadratics, if your slope does not change, if it's not stretched or compressed, you start at your origin and you go up 1, up 3, up 5, up 7. It's speed graphing. This is the parent function. Yep, so this is parent. And now I want negative x squared. So what am I going to do to all my x squareds? I'm just going to make them negative. So now it's negative 4, negative 1, negative 0, which is just 0, right? Negative 1, negative 4, and it looks like this guy. So what transformation happened? This is a reflection over the x-axis is what happened with this one. So here's our parent. They use p of x, so here's p of x showing how it changed to go down there. Okay. Again, the table, not needed, but it's just a good strategy if you need it. All right, ready for that last little bit? All right. Here we go. Another way to transform the graph of a function is to multiply all of the y coordinates by the same positive factor. When the factor is greater than 1, then the transformation is a vertical stretch. When the factor is greater than 0, but less than 1, it is a vertical shrink. So a vertical stretch is what will make it be more narrow. A stretch, I can't write. A stretch is what makes our graph more narrow or skinny. Okay, and a shrink, which is also sometimes called a compress, makes it wider. Okay. So this is if the value is, remember, is bigger than 1, and this if it's in between 0 and 1. Let's try that again. There we go. Why do I have to say it has to be bigger than 0?
Because we can't, get it more from 0 than it's just 0.
Yeah. But how come I can't just say anything less than 1? What's up?
That includes negatives.
That includes negatives. And what are negatives? They're reflections. They're their own thing. Okay? So if there's a negative, that's a reflection. That's all you worry about it. The actual number itself, look at, is it more than 1 or is it less than 1? Okay? But bigger than 0 still. Okay, so we have example 4 to match with this one. Our first one is 2 times the absolute value of x. So let's graph the parent function first of absolute value. I'm going to do a little chart again because it helps me, but if you don't need it, that's fine. So in absolute value, I'm still going to go from -2 to +2. I go a little bit down, a little bit up on the x-axis. Absolute value is all the positive numbers. So there's your parent function. It starts at the origin, and my lines just have a slope of 1 going both directions. That might be something you already know. But now for the transformation, what am I going to do to each of those values? If there's a 2 in front.
Multiply by 2.
Yeah, we're going to multiply them. So 2 becomes 4, 1 becomes 2, 0 becomes 0, 1 becomes 2, 2 becomes 4. And then when I plot those points, it made it more narrow. Does that make sense? Yes. Is 2 bigger than 1? Yes. So we multiplied by a factor that was bigger than 1, so that is what made our graph more narrow. It essentially changes the slope, is what's happening. So instead of up 1 over 1, now it's going up 2 over 1. So it's making your slope more steep. So what do you think B is going to do?
Make it wider.
We can assume it's going to make my quadratic wider. So we have the parent quadratic from right above it in example 3. So if you're done with this one right here, 4a, go ahead and graph your parent function for 4b. So the 0, 0, and then 1, 3, 5. Are we okay? Am I confusing anybody? Okay. This was a big struggle last year. For some reason, it was not connecting. So if you are in that boat, please tell me. Right, PJ? Oh, he out. Throw something at him. I'm just kidding. Good morning, beautiful. I'm so happy you're here. If we sleep on the easy stuff, the hard stuff's going to be like extra hard. So this might be easy in review, but when I start to level up, you're going to need to remember this stuff. Does that make sense?
Then he'll sleep.
Okay.
Then he'll sleep.
Then he'll sleep harder. All right, so my next one. So did we already graph the parent function? Looks like this. We're good? So now, instead of 4, it's going to be a what? If it's a 1/2 x squared, it's going to be?
Is the x always going to be the same
I usually keep them that way because it goes a little bit below and a little bit above the origin. So it shows both sides of the graph. So I typically go from -2 to +2. Yeah. So if x squared when x is -2 is 4, what's 1/2 x squared when x is -2? What's half of 4, friends?
2.
2. Half of 1 is 1/2. Half of 0 is still 0. Half of 1 is 1/2. Half of 4 is 2. So does that make it wider? Yes, it does. Just a little bit, but it does. It does become wider. So this essentially makes our slope, see how it's 1/2, so rise over run. The run is now longer than the rise, so that's why it's wider. Because it's running longer than it's rising. So get that done, and I'm about to teach you how to use these calculators. So make sure they're out and ready. So remember, you're using one of mine or using one of these apps. Someone has informed me that this guy right here doesn't do a whole lot. It makes you pay. So that might not be a great one, but I know those two are still good. So Desmos and Calc 84. Or use the one in my room. Okay. Ready? Yes? Okay, our next one. So it says, we can use more than one transformation in a function. Okay, we're going to combine some stuff together. So we know that can happen. And this one, I'm going to show you how we can type it in and how we can see it. Okay, so use technology to graph. G of x equals negative absolute value, x plus 5 minus 3, and its parent function. And then we're going to describe it. Okay, so let me pull this guy up. We good? We all see it? Yes? That's fine. Just push clear under the bottom arrow. All right, so as I push buttons, it's going to highlight for you on the screen so you can see what I'm pushing. When we want to graph, we have to put things in first. If you just push graph right now, nothing's going to be there. So I want you to push y equals. That top left button, and you get something like this. Okay. Let's graph the parent function first. What is the parent function for what we're looking at in example 5? It's an absolute value, so I need to put that in here. And you're like, I don't know how to do that. I know. That math button is going to be your favorite button. This guy right here. It's underneath your alpha button, so it should be underneath the green one. Math, favorite one. Okay. We're going to go over to numbers and see how our very first one says ABS. Guess what that is? Absolute value. All right. So lots of fun things are found in the math menu. We're going to use that button a lot. Push enter. That's what I want to use. Now, how do I push an X? It's the button next to your alpha button. Just an X. Did anyone have parentheses that pop up instead of the bars? Okay. But then it changed? Okay. I want to be able to view key. There we go. This is showing you what buttons I have pushed. So if you're a little bit behind, those are the buttons I have pushed so far. All right, if you have a blinking arrow like that, go ahead and push over so it gets out of the bars. Okay, that is your parent function. I also want to graph the transformation function that they gave me in example 5. So I'm going to go down to y2, and now we're going to type the function they gave me. So it has a negative out front. That negative is down here next to the decimal sign at the very bottom, next to enter. We're doing absolute value again. So my math button, go over to number, enter absolute value. inside of the absolute value bars, it wants x plus 5. So again, that x is right next to my alpha button. And then plus 5. All right, push our arrow to get out of there. And then it wants minus 3. So minus 3. Okay, so make sure your screen looks like mine. I can probably, there we go up a little bit. So what's down here is every button I just pushed. So make sure your equations look like mine. What do you, so people trying to figure it out, what do you think is going to happen? What do you think, Brennan? It's going to graph both of them? What transformations do you think we're going to see? Looking at the equation we just had to type in. A reflection might happen? Translation where? Evan, what do you think? You think it's going to go which way 5? You think so left 5 and down 3? So we can kind of predict what it's going to look like. Are you ready to see it? Ready. See that top right? See that graph button? Push it. So it'll graph what you typed in first. So for us, the parent function was first. If you have a color calculator like this, the ones that can recharge, then you can make them different colors. If you have the one from my room, sorry, they're not that fancy. They're all black. But it does graph the parent function first, and then it's graphing the reflection over. So do we agree that a reflection happened? Yeah, I would say so. Did it move to the left like we thought? Did it go down? Yes, good. But this is just kind of a lesson of how to use our calculator. Since you hopefully one day will invest into one of these guys, I want to make sure you know how to use it. Okay, in your little box where it says example 5, I would just sketch this. It doesn't have to be anything crazy. So I would just kind of sketch this and write parent. And then we went to the left 5, 1, 2, 3, 4, 5. We went down 3. I'm going to put a little dot right there and now make it go up and down. So I would just sketch it like this in that little box. This is what we see. And then make sure you also list what happened. We reflected over the x-axis. Reflect over x-axis. We moved to the left. What was it, 5? And then we went down 3. All right. Yes. Yeah. Shoot the fair full fast. Just take the green. Oops, sorry. Take the green pass with you. All right, we good? What's up?
I think I did it wrong. It looks really weird.
Okay, oh, if your window is weird, good. So if your window, I think your window is just super zoomed out. You can push the zoom button, which is your top middle button. Right here, zoom.
Okay.
Yep. And then see how 6 says standard? So you can actually just push the number 6. And it'll go back to your standard 10 by 10. So if your graph is ever, someone else zoomed in or zoomed out, it's kind of out of whack. Zoom 6 always brings it back to your 10 by 10. What's up? You got an error? What's the error? It tells you. Syntax, make sure you pushed negative instead of minus when you typed in the second equation, because that could possibly be it. Okay. We're good? Moving on. We'll have more practice with these, I promise. All right. Here we go. All right, example 6. The table shows the height y of a dirt bike X seconds after jumping off of a ramp. What type of function can you use to model the data? Estimate the height after 1.75 seconds. Okay, so looking at the information, how could I possibly figure out what function to use? Well, I see X's, I see Y's. I'm going to plot them and see what kind of shape that they make. Okay. Boop. Okay, so we're going to actually plot the table. Okay, we're going to use it, and then we're going to use this little table, the graph that we're going to make, to estimate the height after 1.75 seconds. Okay, so here we go. Scatter plot first. So I already have it there. I think I have one there. No, I don't. So go ahead and draw you a little graph. How come my X values go 0, 1, 2, 3? How did I know how to label them that way? Because my table has seconds that only go from 0 to 2, right? So I don't need to go to 5 or 10. That's too much. I just need to represent 0 through 2. And then my Y's, same thing. I noticed that my lowest was an 8. My highest value was a 24. So I decided to actually go by 5s on my graph. All right, so now I'm going to plot my point. I'm going to have 0, 8. Oh, get my pen. So 0, 8 is about right here. And then 0.5 and 20. Then I have 1 and 24. So that's probably going to be right underneath this mark. I have 1.5 and 20. And then I have 2 and 8. Oh, interesting. What kind of function do we think we're going to use to model this guy? A quadratic. Yes. Yeah, so we've marked our dots. And they are representing definitely a quadratic function, okay? You can kind of see that in your table too, right? See how there's almost a vertex at 24, and then the numbers repeat on both sides? That kind of represents, it could be a quadratic, it could be an absolute value, because there's a reflection across a vertex going on with our values. All right, so we're going to use this. Now we're going to use it to... So we see that it resembles a quadratic function. So we're going to sketch the curve. Give it a little boop. So we're going to use this now because I don't have an equation, right? I can't just type in 1.75 or solve for it, right? We have to use our graph. So after 1.75 seconds, so this is 1.5, right? Do you agree with me? So 1.75 is probably closer to right here. Boop, 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 boop. What height does that represent?
15.
Looks like about 15. Yeah. So I could use this to estimate that the height is going to be about 15 feet after 1.75 seconds. You can always make sure your answer makes sense. Okay? We know 1.75 is in between 1.5 and 2. So literally on my table, I know it has to be between 8 and 20, right? So if I got an answer that was like 3, that would be wrong. If I got 32, that would be wrong. It has to be between 8 and 20. And we got a value of about 15, which fits, so we know our math makes sense. What's up?
So why does 8 feet as the lowest take 2 seconds, but all the other big numbers take less than 2 seconds?
I don't know. Gravity. I don't know. I have no idea. Because they said so. All right. Here we go. I want you to practice using your calculator down here. So, not these. I didn't lock it. So I want you to do number 10 up there. I believe number 10 is the only one I put on your paper. So I want you to practice using technology to graph the parent function. What would the parent function be? What would you even type in as a parent function? Just x. Good, because this is a linear function, right? This is linear. Woo. So we know my parent function is y equals x. So you're going to use your calculator. You're going to graph y equals x. And you can push clear to clear out what you already got in there. And then underneath it, -1/4 x plus 5. Okay? Now don't ask me where is the fraction button, because fractions are the same thing as what? Decimals or division. So push your division button. Or if you want to make that -0.25, that is the same thing. Okay? So practice your calculator. Let me get my timer.
We're trying to graph.
I'm going to bring this back up for anyone who needs it. So go back into y equals. You're going to clear out what is there. Clear. So that just kind of gets rid of everything. So on this first spot, what's happening? I just want y1. Why don't you go to y1? Okay, it really doesn't matter. X. And then my other one is going to be -1/4 x plus 5. I said plus 5. Thank you. So it's okay if I'm not the top, like the first and second one. For some reason, my computer won't let me go to the y1. It doesn't matter. You can put them wherever you want to. So my parent function is going to be red, and my transformation function is going to be black. So there's my parent, and there's my transformation. Yes. Yes. My parent is red up there. My parent's the red one. Yep. Mm-hmm. Okay, so you have zoom 6. Just push. You can push 6 or you can hold 6. There you go. There you go.
Thank you.
Yep, you're welcome. All right, so that was our calculator practice. Now we have to actually list what happened. What happened to my parent function? It went up how many? It went what? What? It went up 5. All right, what else? And it reflected over the x-axis and
divided by 4.
So how do we, what kind of transformation does that describe? A vertical what?
Shrink.
A vertical shrink. Good. So, I got you. We're going to say, oh, hold on, go back. There we go. So we're going to say that there was a reflection over the x-axis. That's what the negative did, right? And then there is a vertical shrink. That was the 1/4. And then it went up 5, and that's the plus 5 on the end. All right, my last one. All right, the table shows the amount of fuel in a chainsaw after X minutes. What type of function can you use to model the data? When will the tank be empty? Okay, so let's look at it. My X's go 0, 10, 20, 30, 40, okay? And my fuel goes 15, 12, 9, 6, 3. It doesn't tell me I have to plot points. Do you need to plot points? What kind of function do you think is going to be used here? Brennan?
Linear,
A linear, how do you know?
because each, from 0 to 10 is minus 3, from 10 to 20 is minus 3, from 20 to 30.
Yeah, good. So we have a constant rate of change. Remember that fun word? So our X's are constantly being added by 10, and my Y's are constantly going down by 3. So this is showing a slope. We have a line going on. So this is linear. Okay. Now it wants to know when is the tank going to be empty. So it wants to know when the fuel equals 0. How could I figure that out? Yeah, we could literally go one more time. 3 minus 3 is 0. So what's the top going to be? 50. So it's going to be 50 minutes. So this one, we didn't need to plot points. If you wanted to, you could. You don't have to. It didn't tell me I had to. It's just another strategy that we can use. Awesome. Make sure you have your Chromebooks tomorrow. We're going to use them to do some work in our online book.